Hi guys, and welcome to the second biochemistry lecture. Today we're going to focus on water. The big questions that we have to focus on today are: why are you mostly made of water? Why does water function in biological systems, and how does it function? And once again we go to a structure versus function question. How does the structure of water determine its function? So why is water such a big deal? You might have heard a lot about scientists in space looking for water. Frequently when we look to another planet, such as Mars, they're always looking for water because water is frequently associated with life. So, like I just said, water is needed for life on Earth. Earth's very unique in its water for a few reasons. First of all, water is found in both gaseous form, liquid form, and in solid form, sometimes at the same time. You could see if you were to look at the planet from space, it would be mostly blue. How is this water existing? Like I said, we have three different states. The state that you see over here to the left is a solid state, or ice, and you could see that it forms this crystalline structure with space in between it, which will be important later on when we look at it. And this is a liquid form as the molecules slide past each other, forming and breaking apart hydrogen bonds, and as a gaseous state, water is quite far apart from each other. So most of it exists in the oceans. You can see that only 3% of the world's water is in the form of fresh water, and of that fresh water, most of that 3% is contained in ice caps and in glaciers and in groundwater. In fact, only a mere 0.9% of that is actually surface water, and of that, most of that is contained in lakes. Water's unique properties are really based on the function. 3, 2, 1. Water's unique properties are really based on the structure that water has. Structure is made up out of an oxygen molecule bonded to two hydrogen molecules. You could see it sort of looks like a Mickey Mouse here. Now, one of the questions that comes up a lot is, well, why is it polar? Why is it that this oxygen side is slightly negative and that this H side is slightly positive? And the answer really lies in the electronegativity of oxygen. Oxygen is one of the most electronegative elements that we have on Earth. And what that means is that it really wants an electron. It has a strong force of attraction for other molecules' electrons, or other compounds' electrons. So because of this, the electrons that the H is sharing with the O is more closely related on the oxygen side of the compound than it is on the H side. Therefore, with a few more, with the electron being more wanted, and by the oxygen, you have a negative charge over here, and by the hydrogen actually giving up its electron a bit more to the oxygen than it normally would to another atom, you get this slightly positive end over here with where the H atoms are. Okay, because of this polarity, you get water acting like a magnet. So what happens with magnets? The positive end attaches to the negative end of another, and that's what happens at the H attaches with other O's from the H2O, and you get these bonds called hydrogen bonds. Okay, what kind of properties do we get from these hydrogen bonds? Two of them, cohesion and adhesion. Cohesion is when water molecules stick together. Yesterday when we did the activity on floating a paperclip on the surface, this really had to do with the cohesiveness of water, where water has a high surface tension, meaning things don't always pass through water because the force of the hydrogen bonds are keeping the water molecules together, and they sometimes allow things to even live on top of a surface or float on it the way a paperclip did. The second form is adhesion, and this is when a water molecule will bond to another polar molecule of some different type of compound. In this case here, you can see the water molecule is attracted to the tissue of a tree. And because of this attraction to the tissue, the water molecules move up. And we saw this yesterday when we put the paper in a beaker and we saw the water rise up the paper. Another property is the high specific heat capacity of water. What this really means is that it takes a lot of energy to change the temperature of water. These numbers here have some big scary looking units, but it's really simple. It simply means 4 joules of energy are required to change 1 gram of water by 1 degree Celsius. So you could see water's high specific heat is much higher than alcohol or iron. So why is it so high? Well, remember that temperature is the speed at which molecules move. Water molecules, however, don't want to move very fast or move very slow because they don't want to change what they're currently doing because they have these hydrogen bonds attracting those water molecules to each other. So in order for water to turn into a gaseous state, they have to actually break the hydrogen bonds between them. And water doesn't want to do that because there is an attraction to other water molecules. So what's the big deal when it comes to biology? Well, the first thing we have to look at is this fancy little graph over the Pacific Ocean, and what you end up seeing here is that the cities that are on the coast, like Santa Barbara, Los Angeles, and San Diego, have much lower temperatures than some of the cities that are more inland. And this is just because water is acting as a temperature buffer. When the hot sun hits the land, inland, the land heats up really fast, and therefore you get really high temperatures in the coast of, inland in California. But along the coast, as the water comes and hits the ocean doesn't want to change its temperature very easily. So the temperatures remain really cool. The reverse happens in the winter. So areas along the ocean in the winter typically don't get as cold as inland areas do. The other important one is this picture of me on a vacation in Bali. And yes, I dye my hair and wear a wig to school, in case any of you are wondering. But what this guy is doing right now is cooling off. And he's cooling off in the water. So not only does water cool down the temperature of your skin because the water is generally cooler than your body temperature, but also when the water evaporates off of you, it only evaporates off of you if it turns into a gaseous state. And as it turns into a gaseous state, that requires a lot of energy and it requires a lot of heat. So when the water is on your skin, evaporates off of you, a lot of energy is leaving with that water, and that means that we're going to be a little bit cooler. Okay, ice floats. Solid water is less dense than liquid water. This does not sound very intriguing or exciting in any way because we see this every day of our lives, but it is actually a very uncommon occurrence. You know, we frequently think of when molecules get colder, they get closer together and therefore they get more dense. However, that's not the case with water. Why is that? And again, it has to do with the structure of water and it's being a polar molecule. So if you look down at the bottom here, you can see a brine shrimp that's living underneath the ice. And if you look at the ice, the water molecules are forming this crystalline structure that's actually a hexagon. And it forms this structure because the water is so cold it's not moving a lot. And therefore it stays in this hydrogen bond hexagonal formation. However, in liquid water, the water is moving a little bit more because the temperature is higher, and so these hydrogen bonds are breaking and reforming continuously as the molecules move past each other. Therefore, there isn't this need for this hexagonal structure to take place because the water molecules are still moving and sliding past each other. Okay, water is a great solvent. This is a really big one. There is no universal solvent that dissolves all substances, but water comes really close. And again, it has to do with the polarity of water. Here you could see when salt goes into a container of water, the sodium and chlorine that have these ionic charges are surrounded by water molecules. If the molecules has a positive ionic charge, then you could see that the oxygen molecules bind to it. However, if it's negative, you could see that the hydrogen molecules come and surround it. As water surrounds these elements, it's considered a hydration cell. This is a picture of a protein having a hydration shell form around it, as the protein is composed of elements that have a slightly positive or negative charge, and the water molecules bond to it. Next, water dissociates. One of the problems with water being so reactive is that water will frequently react with other compounds and actually make itself break apart. In this case, sometimes we see that water can actually break apart and form H3O, which is called hydronium, and OH, which is called hydroxide. Now, in pure water, the amount of hydroxide and hydronium are equal to each other. However, if there is a disproportionate amount of either one of them, we either get acidic or basic water. Acidic water comes when we have more H3O ions, and basic water comes from when we have more hydroxide ions. Okay, when we talk about pH, we're really talking about a measurement of how many hydronium ions there are. Okay, now you should be able to calculate the pH or pOH if given the hydronium or hydroxide concentration. If you don't know how to do this, look at your textbook and we'll talk about it in class. So how does that affect biology? Well, unfortunately, biological systems have evolved to tolerate only a very narrow range of pH because in our evolutionary history, the pH levels haven't dramatically changed. Unfortunately, humans are causing some damage. One way that we're doing this is through the production of carbon dioxide in our atmosphere, and this carbon dioxide then gets dissolved in the water and forms carbonic acid. Well, what does the carbonic acid do? One of the big problems that it does is it breaks apart the calcium carbonate in the coral reef, therefore destroying ecosystems that contain about 25% of the biodiversity we have in our world. Any questions? Write them down. Let's talk about it in class. After this lecture, you should be able to answer the questions. Why is water necessary for biological systems? Why is water polar? Can you draw a water molecule, assign polarity to different atoms of the molecule, and show how water molecules hydrogen bond with each other? Can you explain the properties of water as a function of its capacity for hydrogen bonding? Can you provide examples of how each of these properties of water discussed in this presentation are used by organisms to maintain their homeostasis? So again, take a look at these properties and think about questions such as, why is the fact that water is a universal solvent important in a biological term? Okay, let's talk about it more in class. Have a great weekend.